8 and chapter 9 and kind of look at these problems. This is where dimensional analysis is going to come back and just bite you. Okay? You have to understand what's happening within each of these relationships and how we work with them. Okay? So what we're going to start off with is something that's relatively more difficult, because we're not starting with that part yet. What happened when we look at chapter 8 and chapter 9? Ultimately, the only thing that chapter 8 gave you was Avogadro's number, okay, which was a conversion factor, allowing you to convert the number of something, okay, into a mole. What was a mole? Just a really big number of somethings. Okay? That relationship allowed us to come up with some very important ideas, molar mass from our periodic table. Okay? So we could then start to manipulate conversion factors in those fashions. Okay? So if we were starting with atoms or molecules, and we tried to convert to AMUs. What is AMU? Atomic mass unit. Okay? Also known as the mass per atom. So if we take a look at, let's pick manganese, because I looked at that first. If I want to look at manganese, its atomic mass unit is 54.94. And this is where things become kind of confusing. What's our unit that we associate this with? Okay, almost everybody writes AMU. Okay, and it kind of makes sense to write that, but there's some extra interpretation behind that unit that I think a lot of people were missing when we write AMU. Not quite, but you got kind of the right idea. We're saying that there are 54.94 mass units per one atom of, what did I say, manganese? One atom of manganese. Why is that such a big deal? It's a conversion. I can now convert a huge or any number of atoms into a mass. Okay? What's the problem with this conversion, though? What's the mass I'm converting it into? What unit does it say? Mass unit. We don't have a balance to measure a mass unit. Okay? So it's experimentally effectively useless. Okay? But that's what this conversion factor allows us to do. Allows us to convert our number of a particular atom or molecules, okay, into some mass unit. If I wanted to get it into something that was useful, okay, say grams, we'd have to use another conversion factor. That other conversion factor would have to convert AMUs into grams. Do we have that conversion factor? Okay. Arguably, we talked about that a long time ago. Okay, we do have that conversion factor. That's not technically new. Okay? Where was that conversion factor on the test? It was on the very front page. It was given to you. Okay? May not have seen it. That's fine. It's an entirely different issue. Okay? This information is available. Okay? When you do the homework, where was it? This one's actually even more challenging. I haven't been able to find it in the book, actually. It's definitely from found in the lecture. Okay, and they talk about it in a sentence where they bring in these numbers and don't hide it or make it very obvious that it's there. But there's kind of a reason why. Okay, can we measure the mass unit? We can't really measure it. So being able to convert between AMUs and grams, in theory, is a nice thing to be able to do. But why would I ever have AMUs? Why would I ever be in that unit? It's something that I can't ever measure. Okay? I can't even wrap my head around it. It's just, there's some weird shape and it has this weird mass that I call an AMU. Okay? So it's a very odd concept as far as that number goes. Okay? So chapter 8 goes through and spins that a little bit differently and says instead of looking at atoms or a single atom or a single molecule, we end up looking at a very large number of them. And that large number happens to be Avogadro's number, which was our 6.02 times 10 to the 23rd. Okay? Atoms in 1 mole. Okay? And we talked about this in class. If we have 6.022 times 10 to the 23rd, atoms equaling a mole, 1 mole, okay? That number, that conversion, is for all intents and purposes the exact same as the 1.66. Okay? They are the inverse of each other. Okay? And that conversion factor they very clearly state. Okay? So the reason I like this format of the table is it allows us to go through and convert between atoms and mass units relatively quickly without having to worry about adding in some extra units. Okay? So there's another version of it that I would say is more useful. This version itself, anybody recognize it? Maybe it's on the study guide. There was another version on the study guide that had some colors, some reds, some blues and stuff in it. And in that reds and blues one, it uses the 6.022 times 10 to the 23rd. Actually, it doesn't even use it there because we don't need it. Okay? So we can start to pull some other information out of it. Okay? So what do these arrows in between mean? Okay? This double-headed arrow. Okay? Or this one. What is that arrow symbolizing? It's how we can convert between those units. Okay? So this is something the morning brought up. Let's say I want to convert between grams of A and atoms of A. What's the conversion factor? Son of a... There it showed. It showed up. Okay. What's the conversion factor between those two? Okay. You should be saying a fairly long sequence of things. There is no conversion factor between those two. What do we have? We have 2 conversions between those. There is no arrow connecting those two because none exists. We have to go through an intermediate stage. Think back to the milligram to microgram conversion. We don't officially have a conversion between those two, so what did we do? Converted it to grams and then related across. We're doing the same thing here. Okay? So you have to be very careful when you go through and approach these problems. You're not saying, I'm at atoms of A, I want to jump to atoms of B. Okay? That's kind of a sketchy one to do. Let's say grams, AMUs of B. Okay? I don't have a direct conversion between those two. Okay? To get that done, what do I have to do? I have to go to AMUs, I have to go to grams of A, I have to go to moles of A, I have to go to moles of B, I have to go to grams of B, I have to go to AMUs of B. Okay? That was how many steps we had? 1, 2, 3, 4, 5, 6 individual steps. In dimensional analysis, that is one line. If you write really big, maybe 2 lines. Okay? If you go through and solve each of those conversions on their own, that's fine, that works. But you now have 6, I already forgot the number, 6 individual steps that you would have to number crunch through. Okay? Which means you have now 6 times where you could mistype into your calculator and potentially get the answer wrong. Or 6 times where you write the answer down wrong on your paper and then translate it into the calculator wrong. Dimensional analysis allows you to string all of these calculations into one single calculation. Okay? That doesn't make things easier, it just makes things less mistake prone. Okay? So that's one of the reasons why we want to go through and use it. These conversion factors are always given to you. Okay? Avogadro's number, AMUs to grams, both of those were on the exam. What about the atomic mass or the molecular mass? Okay? That's also given to you on the exam. What page was that information found? The last page that had the periodic table. Given to you. Okay? The last conversion factor, which came from chapter 9, the balanced reaction. Okay? That allows me to convert between moles of one species to the moles of another. I cannot do that conversion unless I have a balanced reaction. Without that balanced reaction, there is no way to relate the moles of carbon to the moles of oxygen. I have to have some way to relate those two. That comes from the balanced reaction. Okay? Is the balanced reaction always given to you? No. Is the reaction given to you? Most times, yes. So given a problem, you look at it, you have a reaction outlined in front of you. Your very first step should be balance the reaction. If you know nothing else, balance the reaction. Based on what I saw from the exams, you guys did consistently well with balancing reactions. Okay? You guys seem to have that nailed down pretty well, so I'm happy about that. We spent a lot of time with that. That's good. Okay? That definitely showed. You now have to push that to the next step and interpret the balancing of those reactions. Okay? So we have to interpret and then apply to a new problem. Lots and lots of work. Okay, so let's look now. There we go. Simple example. Harry has 100 pennies. Douglas has $3 bills. Sally has 30 dimes. Harry wants to exchange his pennies for dollars. Douglas is infatuated with silver things, and so only exchange his dollar bills for silver objects. These people exist, right? What does Harry have to do to get his pennies converted into dollar bills, and how many dollar bills can he get? Anybody have the answer?
Sally 100 pennies, turn for the dimes. You want to get $1.
So we can get $1, or Harry can get $1 out of this. And to do that, he has to give his pennies over to Sally, get dimes, then give those dimes over to Douglas to get his dollar bill. How many of you wrote anything down to solve that? Do it in your head? Cool, brain's a pretty powerful thing. It does a really good job at processing things that it has done for the last probably minimum 18 years. Okay? How long have you spent studying chemistry? Okay. Not even 18 weeks. Okay? If you really want to push it, it sounds like some of you are getting a bit feisty there and saying 4 weeks. Okay, hopefully it's a little bit more than 4 weeks, considering we're in, what, the 13th week of class? We have to come up with some way to formalize how we went through and solved this, okay? So it's kind of a random side note. You see these types of problems show up in mathematics all the time, and everybody goes, I don't care when the train A leaves station B to get to station Y, and I don't care who it meets and why. There's no way Harry would have to go to Douglas. Harry's just going to say, Douglas, you're an idiot, and go to somebody else and get $1. Okay? This problem never exists in real world. You're true. You're right. It doesn't. What happens if we change the units? Okay? Do you know a natural instinct to do this conversion? No. You have to now have a formalized notation that allows you to do that conversion. That is what dimensional analysis does for you. Okay? It organizes how you work through your calculations so that you can go through and solve things. Okay? So if we change it around to now looking at Snorlaxy and Skittle farts, this becomes an exceptionally funny and difficult problem to deal with. We have to come up with a better way to phrase it. And since, as I found out this morning, I can't even attempt to try and solve it, at least out loud with those words, I'm going to have to switch it back. And let's go through and try and formalize how we approach this problem. Okay? Using the exact same rules that we've gone through and done with everything else within dimensional analysis. To start all dimensional analysis problems, what do we start with? It's not necessarily a bad place to start, but we've definitely been saying something else. Where do we typically start? We start with what we want for our answer. So our equals, and what do we want as our answer? We want dollar bills. Dollar dills. That's still a D. B, there we go, dollar bills. Okay. Now I would argue we can go in with where Sean's suggesting we go with. Where do we start? Or now our next step. We start with what we're dealing with, our 100 pennies. I'm going to make the argument right now that that 100 is irrelevant. Okay? What you should be focusing on is not the number. Okay? Because when you go to enter things into the calculator, it gives you numbers. The calculator does an exceptional job of giving you numbers. What does it not give you? Units. So let's, instead of looking at numbers, look at our units. We are starting with pennies. Okay? Do pennies equal dollar bills? No. So what we have to do is do a conversion. Okay? We have to convert those pennies into dollar bills. So our first attempt is saying that we have pennies. Why do we put them in the denominator? So the units cancel out. What do we want as a target? Dollar bills. Okay? Every problem, we're doing the exact same thing. Now we have to think, and this is where it can get a bit tricky, particularly because our mind is going to mess with us right now. Do we have a conversion factor between dollar bills and pennies?
Yes.
Does Harry have a conversion factor between dollar bills and pennies? No. Okay? This is why we go through and do these stupid word problems. Because we're trying to force you to acknowledge that you do not have this extra information while still making it relevant to you. Okay? So we don't have numbers that we can put into this. So we have to come up with a new thing to work with. Okay? Can Harry convert pennies into anything else? He can convert it into dimes through who? Sally? Yeah. Okay? And again, we could go through and put in numbers. And I'm going to argue yet again, don't. Let's make sure that our units work. So we'll move to our next, well, not even moving to our next conversion yet. I'm jumping the gun. If we look at our units, pennies cancel, and we now have dimes. Do dimes equal dollar bills? If I give you a dime, is that the same as a dollar bill? No. Do dimes equal dollar bills? No. Can we convert dimes to dollar bills? Yes. Okay, you have to be careful with the question being asked. We don't want dimes in our answer, so dimes need to show up where? In the bottom. Okay. What needs to show up on top? Dollar bills. Now when we go through and track our units, our dimes cancel, and what units do we have? Dollar bills. Now that we know we've got our units set up to work, now we can go back through and put in our numbers. What's the relationship between dollar bills and dimes? 1 in 20. There are 10 dimes and $1. Nickels, that's where you got 20. Okay, that makes more sense to me now. Okay. How many pennies? What's the conversion factor between pennies and dimes? 10 pennies and 1 dime. I heard a lot of 10 to 1s. Okay? Not that that's necessarily wrong, but there's an issue with that. No. I think I know where you're going with that. If you say 10 to 1, okay, first number that you put in goes where, typically? Where do you like to put your first number? On the top. You said 10 to 1. Where's your 10 show up? On top. Is that where it's supposed to show up? No. What's the conversion factor between dimes and pennies? 10 pennies is 1 dime. The unit drives your conversion. You must track the unit. Okay? If you don't follow the unit, it doesn't matter what you know about the numbers, you will get it wrong. Okay? Last thing that we can put in here, how many pennies do we start with? 100. Look at that. 100 divided by 10 is? Divided by 10? 1. What did we say the answer was? 1. Everything matches up. The reason we go back to these types of problems and use this as an example, both in mathematics and even now in chemistry, is we're trying to get you used to that format, okay, so that you can go through and do these conversions. Because what happens when we change it up and we bring in these weird units that nobody's ever heard of? You now have to apply that same basic understanding of how you did those conversions and make sure you translate those numbers in correctly. If you don't translate them in, you lose out. Okay? So let's take this a step further. And that first question, I still don't know what exactly I was trying to say there. I think I think there's just a verb tense issue. We'll rephrase that question in a second. Can we put this into a reaction equation? Okay, yeah. What did we start with? What was our reactant? Oh, shoot. We got that one up there, don't we? Okay. We started with, it's actually Snorlax I for the random brain literate. Okay. What are we converting those into? Skittle farts. Wasn't that funny? Maybe it was. It's just a funny word. Okay, we're trying to get that converted into our Skittle farts. Did we need anything to get this reaction to go? We needed dimes. Did we consume dimes? Did we produce dimes? No. So dimes acted as a catalyst. We can put our catalyst above our reaction arrow. Cool. Okay. After all of that work that we went through and did, we could also now start to incorporate some extra information, coefficients into balancing this. How many Snorlaxi did we start with? How many Skittle farts did we end with? 1. Okay. We now have a way to convert Snorlaxi to Skittle farts through the reaction equation without having to deal with all the other weird stuff. Okay. Which is what we're trying to do with chemistry. Okay? Do you guys know specifically how carbon changes its structure so that instead of reacting with 3 oxygens, it reacts with only 2 oxygens? Okay, I'd have a hard time explaining that one. Okay, we don't know that information. So what we've gone through and done is written a reaction equation that allows us to look at and kind of address what the overall changes are without having to get into the nitty-gritty of specifically what's happening in each of those cases. Okay? So what's the unit in this question? This is where it gets a little bit tricky. Okay, if we switched it up a little bit, we can even go back to get rid of our Snorlaxi and Skittle farts, because that's a little bit difficult to interpret. Let's stick with pennies and dollar bills. Is it a volume? Are we measuring the volume of pennies? How about the mass? We're measuring the number of pennies to do this conversion. Okay, so our unit is a very odd one. It's a number of these things to do the conversion. Okay? Our equation is still valid, okay, with that number. So now let's push it to this next question here. What if we change the unit to mass? Okay? Is a dollar bill exactly 1/100th the weight of a penny? Okay? If we came in and said, here's 100 pennies, or 100 grams of pennies, give me my $1. Okay? We're probably not going to get the right conversion factor. The mass does not relate. What are we relating in this equation? The number of these individual species. It has nothing to do with the mass. So if I now want to bring mass into it, what do I have to do? I need a conversion factor that allows me to convert between mass and the number of things. That is what our periodic table is for when we're looking at chemistry. Okay? It is challenging. It requires some practice to get through and do. I know that you guys can do it because I saw that you guys could do the balanced equations. You guys did an awesome job with that. Okay? So I know you can pick up and figure out what's going on with these conversions. Okay? So now let's push it a little bit further. Okay? We brought up a new conversion factor that relates or changes the numbers around. Okay? The reason we did this is because when we look at the numbers within an individual reaction, we need a massive amount of these individual atoms or molecules to do an individual reaction. And instead of always having to carry these powers of 10s all the way through all of our reactions, we went through and converted it and said, you know what, I want a new unit, we're going to call it a mole. that mole is going to represent this number of particles. This now drastically simplifies the numbers that I have to put into the calculator and also simplifies the numbers that I have to write down because I'm ultimately lazy. Okay? So let's take a look at our conversion. First question. Okay? This first question is actually a tricky one. We need to convert what is written in words into our mathematical notation. Where do we start all dimensional analysis problems? The end. Equals. What units are we looking for an answer? Okay? And here's where it's going to become really, really important. Moles is not a complete unit. Moles of specifically what we are looking at. Okay? Because if I write moles of aluminum, can you solve that first question? No. Okay? So you have to be very, very specific about what's actually being happened or what's being converted. What is our specific unit? If we were going to circle it, where's our unit identified?
Wait, are you looking for atoms?
Oxygen atoms. So here's where it's going to become really important. Our formula that we use to say our moles of had better accurately reflect the formula for oxygen atoms. What is the formula for oxygen atoms? O. Why is it not O2? How many atoms are in O2? 2. What did we ask to solve for? The atom. An atom is by definition 1. If I'd asked for the element of oxygen, okay, this question very specifically asks for oxygen atoms. You need to answer the question based on that. It is moles of a single O. Okay? Because the formula O2 now has 2 atoms in it. That is not an oxygen atom. Okay? So what do we start with? Of O2. Okay? We want, oh, that was your issue. That's what you were addressing, Michael. I see your point now. What's our answer unit? Yeah. I just looked at the unit match and realized that we wrote that down wrong. Why is it really helpful to write units? Guess what I was able to see because I wrote units? A mistake. If you don't write the units, we don't know that a mistake was made. Okay? How can we convert our atoms across? Or get to atoms? Well, we're going to go back to our calculation and say we need to do some conversion. Why do we need to do a conversion? This says moles of O2. What are we trying to get to? Atoms of O. Are those units the same? Nope. So very clearly we have to do a conversion. So, does our moles of O2 exist in our answer? No. So that needs to be gotten rid of. Okay. What do we want for our answer? Okay. Is there a conversion factor between this? Avogadro's number converts 1 mole of what? Of whatever. So let's say it's O2. 1 mole of O2, and it converts it into 6.02 times 10 to the 23rd atoms of O2. Does that conversion factor work?
No.
Why not? Look at our units. We're looking at oxygen versus O2. That conversion factor does not translate for us. So we're going to have to do some extra conversions. We don't have that relationship. Okay? Do we have something else that we could go through and relate? Can we convert the moles of O2 into, say, maybe molecules?
Yeah.
How would we do that?
Isn't it
wasn't trying to tell you were wrong. You're right. We use Avogadro's number in this case. Why can we use Avogadro's number? Because our units match. We are looking at O2 in both cases. What would our unit then be?
So 6.02 times 10.
We'll get to the number later. Okay, I want to address the units first. What are our units? Molecules of O2. Is that our answer? No. So again, we need to get rid of that unit. What answer do we want? Is there a relationship between the atoms of O and molecules of O2?
Yeah.
What's that relationship?
2 oxygen atoms, 1 molecule.
There are 2 oxygen atoms for every 1 molecule of O2. So what we need to do is now start to incorporate our numbers. 2 atoms of oxygen to 1 molecule of O2. When we go back to our next conversion factor, where does our 6.022 thing show up? Y on top. What's that? Yes, I hear what you're saying now. We're tracking the units. The 6.022 goes in front of atoms, which could just as easily be molecules. Why would we switch back and forth between those two? If I look at a single atom, what unit do I want to use? Atoms. If I look at a molecule, what unit do I want to use? Molecules. Okay. What we're looking at is any single unit, a count of those units. A dozen cars is 12 cars, just like a dozen eggs is still 12 eggs. Okay, so we can take advantage of switching between those units. Okay? What number shows up in front of our moles? Where's my calculation? 1. How do you know it's 1? You go back to your conversion factor. What number shows up in front of moles? 1. What happens now? Now we punch it into the calculator and we get our answer. Okay? When did numbers show up? At the end, once we knew what to do with the numbers. If you start to manipulate the numbers before you know what to do with them, you will get the answer wrong. Okay? So, follow your units, let the units do the work for you. Should we take a look at the next one or move on to a more difficult one? Okay, I heard a mix of both, so I'm just going to show the units. We're starting with atoms of aluminum. And I want as an answer, I already forgot, moles of aluminum. Again, conversion factor. I want to get rid of my atoms, and I want moles on top. Do I have a way to relate atoms and moles?
Yeah.
Yes, Avogadro's number. Now I can go through and plug in my numbers. Why does the 6.022 times 10 to the 23rd show up on the bottom? Not because I want to get rid of the atoms. That has nothing to do with it. The 6.022 times 10 to the 23rd in our conversion factor shows up in front of what? Atoms. Why does our 6.022 show up in the denominator? Because that's where the atoms are. Okay? Follow the units. Okay? And then we can put in that big, wicked, long number, whatever that is, which I'm attempting to scribble, but it's not scribbling. There we go. Times 10 to the 21st. Okay? And we then punch that into our calculator and we get our answer. Okay? One quick thing, because I talked about it with morning, 10 to the 21st. What do we expect as far as the size of our answer to be? 10 to the 21st, big or small number? 10 to the positive 21st is a very big number. How about 10 to the 23rd? It's bigger, still a really, really big number, right? What are we doing mathematically with those two numbers? We take 10 to the 21st and then we divide by 10 to the 23rd. Ballpark estimate. We take a big number, divide by a big number. What do we get? A million divided by a million gives me 1. Our order of magnitude should be darn close to 1. Okay? We can take further approximations by looking at our 10 to the 23rd and 10 to the 24th to decide roughly how many decimal places it should shift off of that. That's an entirely separate issue. Why do I ask this question? Because when you punch it into the calculator, a lot of people are getting 10 to the 46th. Our estimation skill, what did I say? Skill. Our estimation says it's close to 1. Okay? 10 to the 46th, is that even remotely close to 1? No. What does that mean? You did something wrong. Okay? If you're getting something that far off, usually it's a calculator mistake. Go back and try and re-enter it into the calculator. That quick estimation skill might even eliminate some answers. Okay? In fact, it very easily did on this exam. Okay? Because I know people are making this mistake. So you have to do the math right. Okay? So, next big thing that we address is that we can get the molar mass. Okay? And this was one of the big conclusions that we get out of using Avogadro's number, is we could start to simplify a couple different calculations, and we end up with our molar mass. Okay? Molar stands for really big tooth. Moles. Come on, that was funny. Molar stands for moles. Mass is our grams. So a molar mass is a way to relate grams to moles. That's what our periodic table gives us. Same thing that it did for effectively our atoms. AMUs was a mass to one atom. What is a molar mass? The mass to a mole of atoms. It's the exact same idea. We are relating mass to a number of things. Huge, huge, huge conclusion for us. And the reason we want to use molar mass is because now instead of using this wickedly stupid unit of mass units that we can't measure, what do we now have? Grams, which we use all the time. Okay? So that's the intent and the beauty of ultimately using our molar mass. Okay? So this allows us to convert now mass to moles without having to deal with these weird AMUs. Okay? So let's take a look at a mole to mass conversion. If we start with the mass in grams of copper, I got to read the question. What is the mass in grams of 0.0? It's been a long day. 0.532 moles of copper 2 nitride. Okay, so where do we start all problems? Okay, probably in the government, right? Okay, I got a better laugh there. That works. What do we want as an answer? We want grams of copper 2 nitride. Okay, so I'm going to abbreviate copper 2 nitride as just CN because I'm a little bit lazy. Okay, we're going to have to be a little bit more specific with that in just a second. What do we start with? 0.532 moles of our copper nitride. Okay, are moles equal to grams? No. What does that mean? Conversion factor. Why do I put moles on the bottom? Because it needs to cancel. What unit do I want on top? Grams. So again, we now think. Magic thinking caps. Do we have a relationship between mass and moles? So there's some yeses and nos floating in there. Do we have one given to us? Not really. Can we find one? Yes. Those of you saying yes, how are you saying you can find it? Periodic table. Okay? Which only gets you part way there. So we could go to the periodic table and try and figure out the mass. Okay? Our molar mass. Okay? That's what's shown at the top of this. We're relating mass to moles. So we would go through and add up the atomic or the molar mass for every single one of the atoms that shows up in the compound of copper 2 nitride. Okay? So what's the first thing we add in? Copper. What's its mass? 63.65. I'm looking at cobalt. That's why that's wrong. 63.55 plus what is nitrite? It is a polyatomic ion. This question actually asks two things at the exact same time. What is it asking? How do you do this conversion? And number two, do you know your nomenclature? You will be expected to know your nomenclature. You have to know it. So what we have to do is convert that word, for lack of a better word, into a formula. Is it balanced? Charge on copper. How do you know it's plus 2? The Roman numeral gives us our charge. What's the charge on nitrite? How do you know it's minus 1? It's memorized, or it's given. It's not on the periodic table. Nitrite is a polyatomic ion. Okay? It would have to be given to you as part of your cheat sheet at the beginning of the exam, or I tell you what it was. So we're looking at, whoops, shoot, don't say that. -1, is our charge balanced? No, which means our formula is wrong. Fix the formula. We need a 2 there. So we go back to adding it up. What's the next atom we want to add into this? What's the molecular weight of nitrogen? Why times 2? How do you know there's 2? The subscript applies to what's directly in front of it. What's directly in front of it? Parentheses. Everything now within that parentheses we have twice, or 2 of. So our nitrogen, we have 2. What's our next element? Which is 16 times, why did you say 4? There's 2 in nitrite, and we have 2 of that particular unit. We've got 4. Okay? This gives you 155. Thank you. I don't need any more numbers. I'm bad enough with 3 as it is. Grams per mole. Problem with that. Those are not complete units. Grams needs to be grams of our copper nitrate. Moles needs to be moles copper nitrate. We can now take that information and put it back into our equation. 155 grams. Why did the 155 go on top? Because it's in front of the grams. What number goes in front of moles? 1. How do we know it's a 1? Because it's in front of our mole number in our conversion. Okay? Punch it in the calculator and we now get an answer. Okay? Questions about that? Nope. Can't you just divide it? You tell me. What happens if you divide? Do you get the right answer?
Well, I mean, it's pretty much like saying you have 53.2% of 155 grams.
No, it's not.
No?
What happens if you divide? Do you get the right answer? What happens with your units? Your units do not match. This is why you do dimensional analysis. You follow the units. That sets up your order of operations on whether you multiply or divide. If you go, oh, I just need to divide it. Can't tell you, even in organic chemistry, trying to calculate the number of moles of some species. They go, oh, you just divide by the molecular weight. What happened? They memorized some random formula, and then they didn't apply it to the correct problem because they didn't understand dimensional analysis. Write the problem out. Write the units down. Put the candle back. Okay, some people got it. Good enough. Okay, atom to mass calculations. Okay, now it's a bit trickier. Mass of grams of 2.55 times 10 to the 23rd atoms of lead. Where do we start? What do we want? We want grams. Grams of lead. We could write out lead or we could write PB. Why would we write PB? Yes, love it. Everybody's getting lazier as the day goes. 5 times 10 to the 23rd atoms lead. Atoms of lead equal grams. No. So what do we have to do? Convert. And again, what we want to go through and do is focus on our units and see what happens. What unit do we want in the denominator? Atoms of lead. Sorry, I didn't mean to change colors, but we're doing it. What unit do we hope to have on top? Grams of lead. Do we have that conversion? No. Okay? Which means we can get rid of our grams. What can we convert atoms to? Moles. Okay? Nice. That works. Are moles of lead equal to our grams of lead? So what do we have to do? We need to somehow get rid of moles. So moles needs to show up in our denominator. What should show up in our numerator? Grams of lead. Do we have a conversion factor between the grams of lead and the moles of lead? What is that conversion factor? The molar mass found periodic table. What's the conversion factor between moles and atoms? Avogadro's number. Was there another way we could do this? Absolutely. I don't want to go through and do it because I want to talk about chapter 9 a little bit. Okay? So what we're trying to do is approach and get those units down and deal with the numbers as a secondary fact. Okay? Because the numbers aren't going to change. What is going to change is where you put those numbers, and that is due solely to the units. So you must track your units. Okay? More problems that you could go through and work. So, chapter 9 really makes it important to talk about a complete unit. Okay? Direly important. I keep emphasizing that with chapter 8 and that material we just looked at. 9 is even more important. Why? 9 takes a look at chemical equations. Okay. What is happening with a chemical equation? Okay, well, with our bikes, we converted bike tires and a frame into a bicycle. Okay, so what we're doing is taking our parts and determining how many things we can make out of the product. Okay, but we can't do that with atoms, right? There's no way that we can take atoms and change how they're arranged in space with a different atom. Right? Can't possibly do that. No one wants to catch that fish? H2CO3. What type of reaction do you think we're doing here? How do you know it's decomposition? You're only starting with one thing, and we have heat.
Oh, sorry, I didn't say that. I know, I was thinking about catalysts for so long.
Gives us H2O and CO2. Okay? What happened in the course of this reaction? I took the arrangement of 2 hydrogen atoms, a carbon atom, and 3 oxygens that were all arranged near each other, and I said, F you, you're separating up. And I end up with now 2 separate arrangements of these things. Okay? We are definitely shifting the arrangement of atoms. What we can now do with this relationship is start to interpret it. What interpretation information do we get? If I give you 1 molecule of H2CO3, how many molecules of H2O can be produced? How do you know it's 1?
Because you only have 2 of hydrogen, there's only 1.
You're all looking at the right idea. What's the number in front of H2CO3?
1.
What's the number in front of H2O? If I give you 1 molecule of H2CO3, you can only generate 1 molecule of H2O because the balanced equation tells you those coefficients. What we have now just generated is a way to convert between one type of molecule to another type. That's pretty huge. What did we end up converting? We converted 1 number of one to 1 number of another. So we could say 1 molecule of H2CO3 into 1 molecule, I'm going to write MLC, of our H2CO3 equals 1 molecule of H2O. Is a molecule going to be particularly useful for us? What's the mass of 1 molecule? Ridiculously tiny. So a molecule is useless. So instead, we want to look at a much larger number of these. Why would we look at a much larger number? So that we can actually weigh it. So that much larger number that we use happens to be 6.022 times 10 to the 23rd, which we then rewrite as 1 mole. I now have a way to convert H2CO3 into H2O through a conversion factor. Massively important. That is all Chapter 9 tells you. That is it. Okay? Sort of. Let me backpedal a little bit. Okay? We will look at some other interpretations of chemical equations that ultimately come from manipulating this thought process. Okay? So let's take a look at some examples. Okay? If you're given 1 mole of nitrogen, how many moles of NO can be produced? Okay, let's switch it up. Maybe let's try an easier question. If I give you 1 mole of nitrogen, or let's make it even easier, 1 molecule of nitrogen, how many molecules of oxygen are required to react with it? 1. Why do you know it's 1? Coefficient says 1. What we did to do that conversion, what was our answer supposed to be? Moles of O2. What did we start with? 1 mole of nitrogen. Are those units the same? Is a nitrogen atom the same as an oxygen atom? No. Are the units the same? No. We need to convert those units. So we bring in our conversion factor. Moles of N2, moles of O2. Do I have a conversion factor between those two? Yeah, from the balanced equation. Okay? Our balanced equation tells us that 1 mole of O2 reacts with 1 mole of N2. The number that shows up in front, 1 and 1. How many moles of O2 does it take? 1 mole. Well, that seemed awfully silly. Let's try that again. Let's look at 2 moles of nitrogen to make how many moles of NO? All right, you can crunch numbers all you want in your head, but what should you do? The long stuff. Yes, write it down. Mole of NO is what we want as our answer. What do we start with? 2 moles of nitrogen. Are the moles of nitrogen the same as the moles of NO? No, we need a conversion. Where does our mole of nitrogen need to show up? On the bottom. Why? So the units cancel. What unit needs to show up on top? Our moles of NO. What numbers, or do we have a conversion that relates these two?
2.
Our balanced reaction, and again we're hearing this 2 to 1 thing. Okay, we talked about that with the 10 to 1. What's the issue with our 2 to 1? No units. 2 of what? 2 nitrogen monoxides, 2 NOs produce or come from 1 N2. So we're taking the coefficients from our balanced equation. 2 goes up in front of our moles of NO. Why? That's what our balanced equation tells us. What number shows up in front of the N2? 1, because the number in front of our N2 in our balanced equation is 1. What's our answer? 4 moles of NO. Okay? This is why we use the equation. The unit solves the problem for us. You must track the unit. Your brain is going to mess with your head right and left through this entire situation if you don't track the units. You must get it out of your head and onto paper. Okay? So, an individual question. Okay? And this is something that's kind of important as far as addressing this. Everybody asks, well, you haven't shown me enough example problems. This one equation gives you 6 conversion factors, which means to give you enough examples for one equation, I have to work 6 problems. No, that's not going to happen. What I'm going to do is give you the tools to follow the interpretation. Set up your equation, set up your balanced equation, and start to interpret what information is provided and organize it in the dimensional unit analysis method to get your units to convert across. There is no way that any teacher can go through within probably even a year, and give you an example problem for every single calculation. It's not going to happen. Okay? I'll work that one in class. What we're going to start with on Tuesday, thank you, is we're going to look at limiting reactant concept with numbers. You guys actually did pretty well with limiting reactant concept on the exam. So we'll actually start bringing in numbers, which means more math. Remember, probably 15 minutes. What do you guys want? Beginning of the class or towards the end of class for your quiz?
You pick it. Surprises.
I'm hearing some ends, so we'll put it at the end. We'll give you 15 minutes at the end